Hello and welcome to The Space Above Us, Episode 128, Space Shuttle Flight 56, STS-57, Hab and Grab. Last time, we talked about the 14th flight of Space Shuttle Columbia, STS-55, also known as D2. This Space Lab mission was flown for the German government, who hopefully got their money's worth from the vast amount of data generated by dozens of onboard experiments since they're picking up the bill. For today's mission on Space Shuttle Endeavour, we'll also be spending some time in a pressurized laboratory module in the payload bay, just not the one you think. It's time to meet Space Hab. The Space Shuttle is a large vehicle. Compared to the capsules of the early 1960s, it's a monster. Over 37 meters long, nearly 24 meters wide, but it's important to remember that most of the space is not usable by the crew, or even pressurized. The crew might occasionally make their way back to the payload bay on an EVA, but they spend most of their time in the relatively small crew cabin up at the front of the spacecraft. The 74 cubic meters of pressurized volume available to the crew may have been 12 times bigger than the meager 6 cubic meters available in the Apollo command module, but those vehicles had very different purposes. Apollo only needed to support a crew of 3 for just a few days, and on one specific type of mission. The shuttle needed to support a crew of 7 or even 8 people while supporting a wide range of missions, so that pressurized volume filled up fast. Because of this, volume on the middeck was at a premium. In addition to crew accommodations like the galley, sleep stations, and waste collection system, there was a long line of experiments waiting to get their little slice of weightlessness. This problem was only compounded as NASA expanded their work with private companies who were hoping to evaluate new products and techniques on orbit. In short, the middeck could really use more room. This is where Space Hab came in. In 1983, entrepreneur Bob Citrin had an idea that will sound familiar to anybody who has visited Space Shuttle Atlantis down at the Kennedy Space Center Visitor Complex. Citrin looked at the Space Shuttle and NASA's bold claims of flights to orbit every week or two, and he saw an opportunity. He approached NASA with a plan to build a pressurized module in the payload bay dedicated to space tourism, flying passengers in the back of the shuttle. NASA said, thanks but no thanks, but maybe we can use that pressurized module for something else. By this time in the shuttle program, Space Lab, the pressurized laboratory module provided by the European Space Agency, had already flown once, proving just how useful the concept could be. But Space Lab was pretty expensive, and it took longer than hoped to get it ready for subsequent missions. So, if Bob Citrin wanted to take his pressurized tourist module and make it a general-purpose pressurized module to go alongside Space Lab, NASA was interested. So far, so good. But what makes Space Hab truly unique isn't the concept or the hardware. It's the fact that it would be developed, manufactured, and owned by the Space Hab Corporation. NASA would just lease it as needed. From NASA's point of view, this was sort of a win-win situation. If Space Hab worked, they would have another tool in the toolbox when planning their missions. If it didn't work, well, that's a bummer, but it's mostly a bummer for Bob Citrin and his investors. Sure, NASA was going to have to help support development to a certain extent, and would pour some resources into Space Hab, but it was mostly a private company building their own product. These days, that doesn't sound that weird. As I write this, NASA routinely pays SpaceX to bring crew and cargo to the International Space Station, with SpaceX retaining ownership of their spacecraft. But this was the mid-1980s. Commercial spaceflight just wasn't really a thing yet. The Space Hab company only had 8 employees at this time, so what followed was a twisty-turny tale of studies, contractors, subcontractors, integration testing, and more, told over the course of several years. Some of these subcontractors had also worked on Space Lab, doing more or less the same thing. In fact, there were more than a few similarities to Space Lab, with Space Hab often opting to use the exact same hardware in order to save time and effort on validating new hardware. Space Hab became even more important in the aftermath of the Challenger accident, when President Reagan directed NASA to put more emphasis on facilitating the nascent commercial spaceflight industry. One aspect of this was flying more experiments for companies, and one way to do that was to make a pressurized module for additional experiments, and oh hey, look at that, Space Hab is right here and ready to go. How convenient. In the configuration that we'll be seeing today, Space Hab added 31 cubic meters of pressurized volume to the crew cabin, a 40% increase. And since almost all of this volume could be dedicated to experiments or storage, it quadrupled the available working and storage volume. NASA would hire Spacelab to fly their module in a particular configuration, with the price varying depending on the required capabilities of the module and the number of experiment lockers used. Critically to Spacehab's bottom line, the module could hold more lockers than NASA needed, leaving Spacehab free to lease them out to other companies for a profit. From what I can tell, the whole thing really worked out all around. NASA got an easy and relatively cheap way to expand the capabilities of the orbiter, private companies got more opportunities to fly their experiments in space, and Spacehab earned a well-deserved profit. We'll be seeing Spacehab a number of times over the rest of the shuttle program, so we'll get into more details about it on future episodes. But you can essentially think of it as a cheaper, American, and commercial equivalent to Spacelab. So, let's find out who will be ushering Spacehab into orbit for the first time. Commanding the mission was Ron Grabe, who will be flying for the fourth and final time. We first saw him fly as pilot on the classified STS-51J, then again as pilot on STS-30, helping to send Magellan on its way to Venus. We most recently saw him on STS-42, the International Microgravity Laboratory, where he moved over to the left seat as commander. He may be giving up the commander seat, but he'll stay in the spaceflight world, just moving into the private sector. Joining Grabe up front, sitting on the right, was our pilot for today's mission, Brian Duffy. We last saw Duffy flying as pilot on STS-45, the first Atlas mission, known for firing photon torpedoes at the Earth. Sort of. This is Duffy's second of 4 flights. Behind Duffy is Mission Specialist 1, David Lowe, who we last saw flying on STS-43, helping to deploy TDRS-E. This is Lowe's last flight, but between his 3 missions on the shuttle and the management contributions of his father, George Lowe, during the Apollo era, the Lowe family has definitely left their mark on the NASA human spaceflight program. Moving over to our flight engineer, Mission Specialist 2, and our first of 3 rookies, let's meet Nancy Curry Gregg. Nancy Curry Gregg was born on December 29, 1958 in Wilmington, Delaware, but grew up in Troy, Ohio. She earned a bachelor's degree in biological science from Ohio State University, a master's in safety engineering from the University of South Carolina, and a few years after this flight, a PhD in industrial engineering from the University of Houston. In between all that education, Curry Gregg joined the United States Army, who put her in a helicopter and taught her how to fly it, which she was a big fan of. She would remain with the Army all throughout her astronaut career, eventually retiring after 23 years with the rank of colonel. She got her start at NASA in 1987, working as a flight simulation engineer at Johnson Space Center before being selected as an astronaut in 1990. This is her first of 4 flights. Taking the ladder down to the middeck, we find Mission Specialist 3, Jeff Wisoff. Peter Wisoff, who goes by his middle name, was born on August 16, 1958 in Norfolk, Virginia. He holds a bachelor's in physics from the University of Virginia and a master's and doctorate in applied physics from Stanford. Wisoff's physics career focused on lasers, which, in addition to being a staple of consumer electronics, are useful tools for probing the boundaries of our knowledge about the universe. Just as a fun fact, LASER is actually an acronym standing for Light Amplification by Stimulated Emission of Radiation. Wisoff's laser research touched on a whole bunch of stuff, including reconstruction of damaged nerves and growing and evaluating semiconductor materials. Wisoff put the lasers down long enough to apply to be an astronaut and was selected in 1990. This is his first of 4 spaceflights, but in 2001 he will depart NASA in order to return to his laser roots. He and his wife, fellow astronaut Tammy Jernigan, headed over to the Lawrence Livermore National Laboratory using lasers to study nuclear fusion. Neat. And last but not least, Mission Specialist 4, Janice Voss. Janice Voss was born on October 8, 1956 in South Bend, Indiana, but grew up in Rockford, Illinois. Voss had always been interested in spaceflight as a child, choosing it as a goal at a young age. While on summer vacation, during a fateful trip to the library, she picked up the classic book A Wrinkle in Time by Madeleine L'Engle. The book introduced her to science fiction, which led her to learn more about real science, including the space program, and the rest is history. To earn her bachelor's degree in engineering science, Voss attended the astronaut factory known as Purdue University. From there, she moved east to MIT and earned a master's in electrical engineering and a doctorate in aeronautics and astronautics. Picking up all those degrees took time, and during that time she had already entered the world of spaceflight, working on computer simulations at the Johnson Space Center in the mid-1970s. A few years later, she returned to serve as a crew trainer for entry guidance and navigation. In the late 1980s, she worked at Orbital Sciences Corporation on the transfer orbit stage, which we'll be meeting on our next shuttle mission. She was selected as an astronaut in 1990, and this is her first of 5 flights. The launch was postponed a few times due to delays in launching STS-56 and STS-55, and then again by a few weeks when a high-pressure oxidizer turbopump needed to be replaced. For the first launch attempt, everything was working beautifully, except for the weather. Weather is often a problem for the shuttle program, but the troposphere really had it out for NASA today. Weather was unacceptable at the shuttle landing facility, used in the case of an RTLS abort, as well as all 3 transatlantic landing sites. Just to add insult to injury, the weather stayed on the verge of clearing up for the entire count, leaving an optimistic crew and mission control to wait through the entire 72-minute launch window before finally calling it a day. Ah well. The next day they were ready to try again, and other than a 22-second delay due to a wayward aircraft entering the keep-out area, there were no issues. So on June 21st, 1993, at 9:07 Eastern Time, Space Shuttle Endeavour leapt off of the pad for the 4th time, starting the clock on STS-57. Ascent was uneventful, the crew opened the payload bay doors, and it was time to get to work. Before we make our way back to Spacehab to find out what's going on back there, we're first going to take a look at a payload that's only going to operate for the first few days of the flight. Brought to us by the Goddard Space Flight Center, the Superfluid Helium On-Orbit Transfer Flight Demonstration, or SHOOT, was part validation and part experimentation. The short version of what it was doing was transferring helium back and forth between 2 tanks. But as you might expect, there's a lot more to it than that. Helium is an important element in spaceflight. It's often used as a pressurant in propellant tanks, ensuring that when the prop valves are opened, something actually comes out. But it's also important for extremely sensitive infrared instruments. We don't have time to get into the physics of why this is the case, especially since I don't really understand it, but if you want to make something on a spacecraft really, truly cold, like an infrared sensor, you're going to need helium. But in order to do this, you're going to have to slowly vent the helium out into space. This means that the helium is a finite resource. Just as a concrete example, COBE, the mission to map the cosmic background radiation of the universe, needed to be cooled to just 1.37 degrees Kelvin above absolute zero. That's pretty cold. In fact, since deep space is around 2.7 degrees Kelvin, while COBE was operating, it was the coldest known object in the universe. But since its helium was a limited resource, it ran out in less than a year and could no longer use the super cold instrument. If there was a way to replenish that helium, then that aspect of the mission could keep going. But in order to send up another spacecraft to replenish helium, a lot had to be learned about how super cold, or cryogenic, helium behaved in weightlessness. This is where SHOOT comes in. SHOOT consisted of 2 large tanks, one of which was full of cryogenic helium. Between the 2 was a pipe that the helium could be transferred through. The tanks were nearly identical, except that they had slightly different devices to grab onto the helium inside and move it out of the tank. The validation part of this payload was testing out the mechanisms that engineers had already designed to solve this problem and see how they performed in real-world conditions. The experiment part was basically just keeping an eye out for unexpected behaviors that would help make a more robust model of what this exotic material does in space. For the first few days of the flight, controllers at the Goddard Space Flight Center put SHOOT through its paces, moving helium back and forth at different rates, with different temperatures and different strategies. They also had the crew do it from on board the spacecraft to ensure it could be done without ground support. The crew also obliged by supplying a couple of thruster pulses to see how SHOOT behaved when it was being jostled around by spacecraft accelerations. The Goddard team did indeed see some unexpected behavior, but sort of counterintuitively, that was expected. They didn't know what they didn't know, but they knew it was something. All in all, the experiment was a big success, and it was shut down on flight day 3 in anticipation of our next topic, Eureka! No, I'm not just saying that. I'm talking about the European Retrievable Carrier Satellite, which we deployed almost a year ago on STS-46. Eureka was sort of a standalone version of Spacelab and LDEF combined. It was loaded with all sorts of experiments that would benefit from an extended stay on orbit, along with a smoother day-to-day environment than the shuttle could provide with its various thrusters, crew members bouncing around, and so on. I talked more about Eureka's mission back on episode 121, which covered STS-46, so I'll just get to the matter at hand. It was time to get it back. Eureka had been designed to be launched and returned to Earth as many as 5 times, allowing for hundreds of experiments to be flown for Europe. In anticipation of this retrieval, ESA had lowered Eureka's orbit so that it was easier for Endeavour to get to it, and Endeavour had performed several burns to begin closing in on the science spacecraft. The final approach came on flight day 4, with only a couple of minor hitches along the way. As pilot Brian Duffy tells it in an oral history interview, he made a somewhat embarrassing, if ultimately harmless, error. I still have a lot to learn about how to actually operate the shuttle, but one thing that always strikes me is just how manual it can be. As a software guy, this kind of makes sense to me. With something as complex as the shuttle, every extra bit of software just adds to the complexity and hides more functionality out of sight of the crew. When you have an extremely smart and well-trained user base, aka astronauts, you can count on them to just do things right. Well, the corollary of this is that it's possible for the astronauts to do things wrong. And in this case, while entering a value into the digital autopilot, as Duffy was punching in the value 0.5, he apparently didn't push hard enough on the button for the decimal point. And this also makes sense, since the last thing you want is a button that's easy to punch by accident. But the result was that instead of typing 0.5, he just typed 5. Commander Grabe at the controls suddenly was getting thruster pulses that were 10 times bigger than he expected. As Duffy tells it, everybody immediately knew the mistake that Duffy had made, but Grabe just recovered without making any comment. Duffy fixed the error, and the rendezvous continued. Duffy apologized, and Grabe just said, "Hey, we got it. Don't worry about it." So, it sounds to me like Ron Grabe was just the type of boss that everybody hopes to get. One other hitch was that while Eureka was able to fold up its solar arrays and antennas, the indication that the antennas were latched into place never arrived. The antennas were almost in the correct position, but they were off by a few degrees, and they weren't locked into place, and they had the potential to move on their hinges. After some quick consultation with the ground, it was determined that it should still be possible to berth the spacecraft, even with the antennas partially unlatched, so the capture could continue. 3 days and 46 minutes into the flight, David Lowe operated the remote manipulator system and moved in for a nice and easy capture of Eureka, later singing the praises of Commander Grabe's piloting skills. He said, quote, "Ron basically eliminated any relative motion so that Eureka was just rock solid." Immediately after capture, one last little hitch appeared. The end effector of the robot arm, essentially its hand, was a special one that was able to transmit electrical power to its target. This was potentially important, since Eureka had stowed its solar panels and was now running on battery power. If there was a problem berthing the spacecraft, or a problem with the berthing umbilical, Eureka would be stuck without a source of power. The special end effector was supposed to be able to power the spacecraft in the meantime. The crew tried the malfunction procedures, but they just couldn't get the end effector to work, so shrugged and moved on with the berthing. Thankfully for Eureka, berthing it in the payload bay went smoothly, and the umbilical provided power with no problems. After returning to Earth, the cause of the end effector power problem would be revealed as one that happens more often than I would expect in spaceflight. The device was installed upside down. Whoops. Eureka is one of only a handful of satellites that has ever returned to Earth intact, thanks to the unique ability of the Space Shuttle Orbiter. It was designed to fly 5 times, but due to budgetary constraints, the 11 months it spent in space on this mission would be its last. These days, you can go say hi to it in the Swiss Museum of Transport. If you do, send me a picture. I realize that we still haven't discussed much about what we're actually doing in Spacehab, but those loose antennas are making me nervous, so we should probably go do something about that first. The only way to latch the antennas firmly to the side of Eureka would be to go outside. But it just so happens that that's exactly what we were planning on doing anyway. As I mentioned a few episodes back, NASA was making a concerted effort to get more experience with extravehicular activity. They were mindful of the huge number of EVAs expected to assemble a space station in a few years, as well as the high-profile servicing mission of the Hubble Space Telescope in just a few months. The only way to gain more experience in something is by doing it. So NASA had planned a number of spacewalks that were essentially just dedicated to doing spacewalks. This was great news to David Lowe and Jeff Weissoff, who learned late in their training that they would have the opportunity to head outside. While gaining more experience is a worthy cause, it also wasn't a super high priority for any given EVA. So for this mission, the crew wouldn't know for sure if an EVA would even happen until after they had arrived on orbit and ground engineers could confirm that Endeavour had the required resources to remain on orbit for an extra day. Put another way, the nominal plan was to perform a 7-day mission with no EVA, but everyone was working as hard as possible to make that an 8-day mission with an EVA. And sure enough, on the first day of the flight, the EVA was given the green light. In order to prevent disruptions to the science experiments being carried out on the middeck and in Spacehab, the cabin pressure would remain at sea level for the entire flight, requiring the EVA crew to pre-breathe oxygen for 4 hours, purging nitrogen from their blood. After hours of pre-breathing and equipment checks and still more time being crammed into the airlock, on flight day 5, David Lowe and Jeff Weissoff climbed out into the payload bay. Their exit from the crew cabin was another first for the shuttle program. Due to Spacehab's presence, the normal airlock exit was occupied by a pressurized tunnel. So instead of climbing out of the back wall of the middeck, they popped out through a hatch on the top of the tunnel. First on the agenda was to make their way to Eureka and help get the antennas latched in place, which was completed with no difficulty. Once Eureka was taken care of, the duo could focus on their EVA tests, which were pretty similar to those on STS-54. They practiced moving around the payload bay, managing their tools and safety lines, and carrying each other around to simulate the task of moving large heavy objects. Since much of the Hubble servicing mission would be performed by crew members whose feet were attached to the robot arm, this crew also practiced a series of tasks involving the arm. How quickly can they move the arm while they're carrying something heavy? Can they precisely move big heavy things around from their robotic perch? Stuff like that. Other than the Eureka antennas, the EVA didn't really accomplish anything concrete. But I think that these let's just learn what we're doing spacewalks are kind of neat. They added 2 more people to the ranks of the astronaut corps who had been outside. They produced more feedback on what worked and what didn't work in training. And they had invaluable experience for all the people on the ground who support the 2 people who get to go outside. While Lowe and Weissoff enjoyed themselves outside, the crew members who stayed inside had a heart-stopping, if ultimately harmless, moment. At one point during the EVA, the belly of the orbiter was facing the sun, leaving the payload bay in shadow. Grabe, Duffy, Curry Gregg, and Voss were up on the flight deck helping to support the EVA. Suddenly, as Duffy tells it, quote, "All of a sudden, it was as if somebody took the orbiter and hit it with a bulldozer or something. The whole vehicle just went thong. It just shook." The startled crew looked around at each other, wondering if they had just been hit by a piece of debris. But there were no alarms going off, and there were no chunks of the wing floating by, so clearly that wasn't it. Duffy continued, quote, "After a while we said, well, maybe we ought to tell the ground about this." The eventual consensus was that this was a phenomenon seen on a couple of space lab flights, which use a similar pressurized tunnel. Some combination of the heavy tunnel relaxing in the microgravity environment, combined with the harsh thermal conditions associated with being in shadow, just caused it to sort of pop and shift, rattling the entire vehicle. According to Duffy, the EVA crew never heard a thing, but if they had looked back in the flight deck windows at that time, they would have seen 8 big eyes wondering what the heck had just happened. I'm sure they all heard about it after they clambered back inside after their successful 5-hour and 50-minute long EVA. Okay, with Shoot wrapped up, Eureka captured, and the EVA completed, I guess we can finally take a look inside Spacehab to see what's going on. Just like Space Lab, in order to get to Spacehab, the crew would head down to the middeck, enter the airlock, and float down a pressurized tunnel to what was basically just a big room, but not quite as big as Space Lab. Both these systems use multiple modules that can be connected together, with each module taking up the full width of the payload bay and being about 2.7 meters long. But Spacelab would typically fly 2 modules, for a total length of around 5 meters. For this flight, Spacehab is only using a single module, so it's only about 2.7 meters or 9 feet long. But with pressurized volume at such a premium, that relatively small addition still made a big difference. One other notable difference between the 2 module systems is that Spacelab was a cylinder with big domes on either end. Spacehab had a flat top and had flat end caps. The flat end caps meant that more stuff could go into the payload bay, and it made it easier to mount stuff onto the walls. And the flat top meant that in the unlikely event that a contingency EVA was needed to close the payload bay doors, an EVA crew would be able to scoot between the doors and the flat top of Spacehab and get back to the airlock. Inside, we find the usual slew of experiments that we've grown accustomed to seeing on the middeck and in Spacelab. Growing crystals, studying special polymers, testing plant growth systems, examining hormones in rats, the greatest hits. One notable experiment tested a system for recovering water from the air and from wastewater. As distasteful as the thought of drinking recycled pee might be, it was an absolute necessity for a long-lived space station. Otherwise, the majority of shuttle payloads would just be dedicated to bringing up more water. Don't worry, though. I can't speak to this early test version, but the system used on the ISS today puts out nothing but pure water, with some astronauts saying it actually tastes better than the water brought from the ground, which tastes like the plastic bags that they're shipped in. If you say so. All in all, Spacehab was a big success. One of the biggest issues was that the environment inside was slightly colder than expected, which is a pretty minor problem. Plus, it turns out that the reason it was that cold was that it was using less power than expected, which I guess is a good problem to have. The flight was originally going to come to an end on flight day 8, but Florida weather was once again, Florida weather. The crew stayed strapped in for one extra rev, and then Mission Control waved them off, giving the crew another whole day on orbit. The next day they tried again, with the same result, making this only the second flight to get 2 extra days on orbit, and one lucky crew. The delay was so long that the crew opened Spacehab back up so they could top off the water supply for the rats, who I'm sure were very concerned. According to Duffy, the last few days on orbit were really special. By the second extra day, they had really run out of everything they needed to do, and got to just spend time enjoying the view out the window. Since they had already used up all the film for the cameras, they didn't even have pictures to take. Duffy and mission specialist Nancy Curry-Gregg went up to the flight deck, turned the cabin lights down, and just hung out in the window, watching the world go by. After the frantic pace earlier in the mission, I'm sure it was a welcome break. But eventually, even the weather in Florida has to cooperate. So on flight day 10, the crew once again closed the payload bay doors, suited up, and got ready to head home. This time, the OMS pods lit up, and Endeavour began the long fall back to Earth. At one point, not long after Endeavour entered the atmosphere, it was traveling at around Mach 22 when something made a huge booming noise. As pilot Duffy described it, quote, "It was like somebody took the rear end of the orbiter and just rang it. Just went wham. It was like we hit a speed bump or something in a parking lot." 30 seconds later, another big boom rang through the spacecraft. Curry-Gregg told Duffy later that she was sitting there on the flight deck and the booming noises obviously caught her attention. This was her first flight, and there had been nothing like this in the simulators. But, lots of things were different on the real flight, especially sounds. After the first big boom, she looked to the pilot crew, who both just kept looking straight ahead like nothing was unusual. Maybe this was just normal. But after the second teeth-rattling bang, Commander Grabe turns to pilot Duffy and says, "Have you ever felt that before?" And Duffy says, "No." And that got her attention real fast. It turns out that what happened was that even in the super thin upper atmosphere, there are still variations in pressure, just like we have on the ground. They're basically like the wind shears that we've discussed being a problem on ascent. And when you're traveling at 20 times the speed of sound, it doesn't take much of a pressure differential to shake things up for you. Especially in the orbiter, because, I'm just going to quote this whole paragraph from Duffy's oral history directly because it made me laugh. He said, quote, It's like somebody really picks it up and shakes the whole orbiter. The whole vehicle rings, because the vehicle's not that sturdy. It looks like this big, massive, sturdy thing. It's about as stiff as a Twinkie, and truth be known, during ascent, you can actually feel it flexing. It's not just made out of I-beams of steel or whatever. So, you heard it here first, folks. Future Space Shuttle Commander Brian Duffy has compared the Space Shuttle Orbiter, a pinnacle of aerospace engineering achievement, to a Twinkie. Well, Twinkie or not, on July 1st, 1993, Space Shuttle Endeavour safely touched down at the shuttle landing facility at the Kennedy Space Center, rolling to a stop and closing out a mission lasting 9 days, 23 hours, 44 minutes, and 54 seconds. This is a nifty flight. It sort of has a piece of everything we've come to expect from the shuttle program. With Shoot, we did some technology demonstrations and explorations to further expand the envelope of what we're able to do in space. We performed a rendezvous and used the RMS to capture a satellite and safely return it home. We did an EVA, including a minor satellite repair. And we saw the budding cooperation between NASA and private spaceflight industry continue to grow. So like I said, it's a nifty flight. Next time. Well, the next flight is STS-51, so we'll be talking about STS-51, right? Yeah, I guess we could do that. But it looks to me that when the payload was deployed from Space Shuttle Discovery, there was some unexpected excitement. So maybe before we dive right in, it would be better to hear from somebody who had first-hand knowledge of the incident. Yeah, I think that's what we'll do. Tune in next episode as we break new ground on the space above us. We'll put down the script and conduct our first interview. Ad Astra. Catch you on the next pass.